so we'll consider what is our free field. Okay, so radiation gauge, it means Coulomb gauge, where phi is equal to 0. So I will explain it. So let's take the Lagrange. So this is our free field, which we try to quantize now. We have actually in the last lecture we have discussed it. We can fix our Lagrange so that you can have a propagator for the electromagnetic field. That fixing of a Lagrange you call it as a gauge fixing, a kind of procedure which fixes the problems of it. Okay, so let me take now the Lagrange. This is our free field. So what is the equation of motion? Those are the Maxwell's equation, that mu is equal to 0. Okay, so we can calculate. Okay, so what is our field at hand? What is the quantization procedure? What you need to take the field at hand. Okay, so what is the field here? A mu. So A mu is our EM field. So let's calculate. Okay, so so let's first calculate its canonical conjugate momentum. So I will write this canonical conjugate momentum. So it is partial L by partial naught A mu. So how much is that? F0 mu. So these things we have been calculating all the time. Okay, so when you have a quantization, it means the dynamical degrees of freedom what you are having at hand are the degrees of freedom which represent your system, are the physical degrees of freedom I should say, which represent your system. Okay, you promote them to the operator level. Okay, or in other words, the variables are the measurable quantities what you are having at hand, observables what you are having at hand, you take them from the function to an operator level. Okay, this is how we do the quantum mechanics. Let's say you are having Q and P describing the position and momentum of the particle. Okay, classical particle. If you want to quantize the motion of that particle, okay, or quantize that very system, you promote Q and P to the operator form. Okay, so here the degrees of freedom which represent our electromagnetic field, they are A and pi. Okay, A is the field and this is the canonical conjugate momentum. You promote them to what? To the operator level. Okay, and then impose the suitable the commutation relation. Samajh? Okay, now the problem is here, if I take, okay, let me take mu equal to 0, so that is 0th component, it is simply equal to F00. What is that equal to? 0. So that means this component turns out to be 0. The canonical conjugate momentum corresponding to A is 0. Okay, so you take the A0 which is our potential corresponding to this canonical observable, the momentum turns out to be what? 0. Okay, so this is the problem and we can fix this kind of problem by gauging the Lagrangian. Okay, or you can impose conditions on the A field. Okay, so much of what we will do. Okay, now we have to these variables we need to now promote to the operator form. Okay, so much of when I promote them to the operator form, then I will impose a commutation between A and pi. But the problem arises, this A naught corresponding to this thing I am having a 0 as a canonical variable. Okay, it vanishes. Okay, so that means what I will do, I will treat this A naught to be a constant function. So what is our A naught? It is our phi, the scalar potential. Okay, so we will treat this phi to be a constant. So okay, so that constant we will take to be equal to 0. So now why I require that? Okay, so what I have imposed a condition. So look, okay, let's take a look other way around. Let me have a commutation between A's and pi's. Okay, so let's forget about the indices. I take the commutation. Okay, now corresponding to A naught, I am having a pi naught. So that's equal to pi naught is equal to 0. What is the commutation? That is trivially equal to 0. And this pi naught will commute with all the other variables. I mean all the other A's. You are having 4 A's, is it? So that means this pi naught will commute with all the A's, is it? So much more similarly, if you take A naught, since A naught, okay, that's equal to phi, corresponding to pi naught is equal to 0, this phi will also commute with other pi's. Samajhan? It is better option to fix the a naught. Okay, so that means we fix this phi. Okay, let's keep this as only the function. Okay, and I am saying this function is equal to 0. Samajhan? So what was that gauge called? Yesterday we said a naught, when it is equal to 0, we call it as an axial gauge. Is it? Samajhan? So that means we impose first condition on our potentials. Okay, so that is, we say this phi is a constant function. Let's put this phi equal to 0. Okay, so that means we are at hand, we are having only 3 variables. Only the vector potential is what? Non-zero. So we are having this a, that's non-zero. Okay, so and corresponding to this a, now let's write pi I. So that's equal to f0i. So how much is that? That is simply ei, the electric field. So they are non-zero, is it? So that means the canonical conjugate momentum corresponding to this vector potential, they are the electric fields. Okay, got it? And this is non-zero, and I can impose, or we can impose, the commutation between a and e. Now let's check what does this exactly mean if I take this phi equal to 0. So we are making a quantization condition when phi is equal to 0. So let's put, okay, this on a strong footing, I mean on a physical footing, what exactly it means to take phi equal to 0. So let's go back to this equation of motion. Okay, so let's look at this very thing. So our condition is phi is equal to 0. Okay, so everybody agrees with this? Okay, good. So let's take the equation of motion. I'm having partial mu. So it is partial mu a nu minus partial nu a mu, that's equal to 0. So okay. Now can anybody tell me? So which term is equal to 0? So let's take nu equal to 0. So let's take nu equal to 0. So what does that mean? So I'm having this partial mu a 0 minus partial mu partial 0 a mu. Okay, so that's equal to 0. Can I write it? Okay, so now this is equal to 0 identically, because a0 is 0. Okay, so what it gives me? So it gives me like this thing, partial naught partial mu a mu, that's equal to 0. So what it yields me? So partial 0, so this I can write partial 0 a0 plus partial, or you can write like this thing. Anybody? Okay, plus or minus plus gradient of a. So that's divergence of a. Is it? Is that true? So now what is a naught? That's equal to 0. So it implies this partial naught del dot E is equal to 0. So which implies this del dot E is actually constant, and that constant is actually 0. So you can show that that's actually 0. So the consequence of this phi is equal to 0 implies what? Del dot A equal to 0. So we have arrived at one more constant equation. Now how many degrees of freedom you started with? 4 degrees of freedom. How many constants you got? 2 constants. Now how many physical degrees? Only 2. Okay, so that means okay, so what does this mean? Del dot A, it means what it gives me, can you tell me? Divergence of A, the field, divergence of field is equal to 0. What does it mean? No. So it's actually the transversality condition of the field. Okay, suppose if you are, let's go to the momentum space. Let's go to the momentum space. So this del dot A, if k is the propagation vector, okay, let's say this is the propagation of the wave. Okay, so along the direction of the momentum, so it is the propagation 3 vector. What this will give me? This will simply give me k dot A is equal to 0. समझ? So that means the proper direction of the propagation and the field direction, they are orthogonal to each other. So it means the transversality condition. समझ? So that means the field direction of the propagation and the field direction are orthogonal to each other. Or in other words, the wave which you get here is what? A transverse wave. समझ? This is simply the transversality condition. We call this gauge as the radiation gauge or Coulomb gauge. So now our radiation gauge is equal to phi equal to 0, del dot A is equal to 0. This is also known as what? Coulomb gauge. Radiation gauge, why can you tell me why we call this as a radiation gauge? Because when you have a radiation, okay, simple electromagnetic wave, okay, emanating from a certain source, let's say, or in the vacuum, what it satisfies? It always satisfies the transversality condition. Clear? So that's why we call it as a radiation gauge. Okay. Okay. So now, if you look at this very gauge, this very point. Okay. So now we have arrived at the constants. Now, if you look at this very gauge, this is actually not Lorentz invariant, because phi is a component of a 4 vector. A is also the component of a 4 vector. Let's say if phi is 0 in one frame of reference, it's not 0 in the other frame of reference. Okay, so let me show you. So since phi is a 4 vector, phi, okay, so you are having this A mu, that's equal to phi and A. So you can see this phi transforms like this thing, gamma into phi minus V by C square. Okay, then you are having this AX. Okay, then you are having this AX prime, that's gamma into the same thing what you are having for XT. So minus V phi. So let's say phi is equal to 0 in one frame of reference, then phi prime is not equal to 0. Similarly, if you are having del dot A equal to 0 in one frame of reference, it's not 0 in the other frame of reference. So that means you have lost the Lorentz covariance here. समझ? Got it? But at the cost of Lorentz covariance, we have arrived at 2 physical degrees of freedom. समझ? Okay. So now what we will do? So we will impose naively. So let's, okay, so what are our degrees of freedom? So our degrees of freedom are this vector A and pi. Clear? So what are those? These are simply, anybody? A dot. So what is our pi? Okay, so we are having this pi. So how much? What is that? So it is simply EI. Clear? Rather minus EI. How much is that? So pi I. Or let me write this vector. So what is that equal to? Minus gradient of phi. Phi is equal to 0. Then it's minus 1 by C. C is equal to 1. So it will be simply partial A by partial P. Okay. So what is that? Simply A dot vector. समझ आओ? Got it? Okay, so I should put like this vector A dot. Okay, so you are, okay, so your physical degrees of, okay, so now you are having 3 degrees, I mean A, vector A. Clear? So you are having A corresponding to a coordinate Q, and then you are having the momentum for that, what you are having? A dot. समझ? So what is now we can impose a commutation relation. Clear? समझ? Let's impose a commutation. Okay. So let's impose commutation relation like this. Okay. So let me write. So we have to take equal times. So it means AI at xt, let's say, and then you are having AJ YT. So the same operator. Okay. So the point is here. So when you quantize the system, you promote A and E to the operator form. Okay. Or promote A and pi to the operator level. Then you can impose a commutation condition. Clear? Commutation can be non-zero only when they are the operators. Now the commutation with itself is equal to 0. So time is same. So we call these as equal time commutation relations. Okay. So this is equal to 0. the commutation of the variable with itself. So let me put for the time being as a cap. So it means operator. Then you are having commutation between this pi I, okay, equal time commutation. So that's equal to 0. Now the non-zero commutation comes from between A and pi. So that's Q and P. So you are having this A I X T. Okay, then let me write this pi j y t. So let's impose it delta. So delta j I delta 3 x minus y. Okay. So there should be I as well. Can you tell me why? It is I h cross. So much out? Iota has to be there. So let's check whether this is correct or not. So much out? So these are the quantization conditions. We need to check whether they are consistent with the gauge condition. So much out? This is the first check. Okay. So the Lorentz covariance is already lost. We don't need to look at the Lorentz covariance because the gauge we have chosen, it does not respect to the Lorentz invariance. Okay. But what we need to check whether these commutations are consistent with the gauge conditions or not. समझ आओ? So forget about these two things. They are consistent in a sense. Let's take that del dot A is equal to 0. When you put del dot A, that del means differentiation with respect to x, let's say. So del dot A equal to 0. So if you put del dot A, this will be 0. Commutation of 0 with this thing is equal to 0. So this is satisfied. Okay, what is the divergence of this thing? Because divergence is on A. So these are pi's, correct? So this is already 0. So this is satisfied. Now let's look at this very object. So I should put a cap here. Okay, so let's look at this very thing. Okay, so let's take the divergence on this thing. So divergence, okay, of the commutation, this A I X T, okay, then you are having this pi. Okay, what is pi? A dot. Pi is A dot. So let me write it as A dot J, okay, Y T. So this is okay. So I will take this divergence as the differentiation with respect to x. Clear? So it will be the differentiation with respect to what on which it will depend. Clear? Okay. So that's equal to now I delta J I divergence of what? This delta 3 x minus y. Clear? So you are taking divergence on both sides. Now if you see what is the divergence of A, so this will be divergence of this A, clear? So this object is equal to what? 0. So that means left hand side is equal to 0. समझ आओ? Now what about the right hand side? This object is not equal to 0. Because this is a differentiation of delta function. It is usually a divergent quantity. समझ आओ? So this is never equal to 0. So differentiation of this delta function is not equal to 0. So that means this commutation does not satisfy the gauge conditions. Okay? So in other words, the way we have written this commutation is wrong. Got it? So we have to fix this commutation so that to achieve a suitable quantization condition. Clear? A commutation. Okay, look at the harmonic oscillator. So, or any kind of particle. So, if you are having x and p, clear? So, quantization means this very condition. I stress. समझ आओ? So, if you impose this very condition on any, let's say quantum, any particle, okay, non-relative particle, so you then say your particle is quantized, or the motion or the dynamics is quantized. Clear? Your system, in other words, your system is quantized. Now the problem with the electromagnetic field, it's a little bit weird field and very difficult to quantize, because I am having many degrees of freedom. I am having only 2 physical degrees of freedom, which is being represented by F4 vector, let's say here. Okay. So for that matter, we are imposing the gauge condition. Now here what I have chosen the gauge condition, which are not, not Lorentz covariant, or which does not respect the Lorentz invariance. Okay, so that means my Lorentz invariance is lost. Okay, but still I want to quantize the system. Okay, so for that matter I have chosen, okay, these set of rules. Okay, because the commutation defines our quantization. So these are trivial. Now let me check whether this non-trivial commutation satisfies the gauge condition or not. So the condition, the constants what you are imposing on your system, you need to check whether they are consistent with what? The commutation, or whether the commutation you are imposing on your system are consistent with what? The gauge conditions. Okay. So this is not consistent with the gauge condition, because okay, phi is equal to 0, because there is nowhere phi. Okay. So it hardly matters. That's okay why we need to take only del dot A. So when you take del dot A, this divergence, so this is equal to 0, but this is not equal to 0. So that means it's not respected, it is violated. Okay. So in other words, what we have to do, we have to actually, rewrite this kind of commutation. Samajh Shaman? You got my point. There is actually a well-defined procedure of doing this thing, but we are doing it quite, in a straightforward fashion. Okay? Samajh Shaman? But there is actually a well-defined mathematical procedure to arrive at these kind of commutation relations. Okay? So let's do it. Okay? So instead of using this very, okay, so instead of using this commutation, what I will do, okay, so delta function has to be there, this delta function, because this delta function arises because of two different space variables, is it? So x and y. Samajh? And this delta ji, if you see, this arises from where? The indices I and j, clear? Samajh? In other words, this is actually rank 2 tensor on the left hand side, because it is the product of two vectors. Okay, and this has to be what? A rank 2 tensor. Samajh? So for that matter, what I will do, so okay, we introduce a rank 2 tensor, delta ij, let's say, okay, such that okay, such that commutation relation 1, let's call this as equation 1, satisfies the gauge condition. Okay, so this way we will do it. What I will write, so let me write this AI xt, okay, then pi j yt, okay, so I will write this as I times this delta ij, instead of that Kronecker delta, I will introduce what? Delta. You will, okay, in a moment we'll see what should be its form. Okay, Samajh? So then this delta 3 x minus 1, like this. So what is our point? So we want to say this delta ij actually removes the problem. Samajh? Instead of using that Kronecker delta ji, I am introducing a new tensor, delta ij. We'll see actually this delta ij is actually the projection of the Kronecker delta along the transverse direction. Okay? So much of, okay, we will see in a moment what does it mean. Okay. So what we will do, so we will write it, okay, transform this delta of x minus y to Fourier space. Okay? So what does that mean? Okay, so let me write therefore AI xt, okay, pi j yt, so that's equal to I delta ij integral So it is a three-dimensional this thing by 2 pi cube. Okay, then e raised power minus I k dot. So this is a vector k x minus. Clear? So now let's take the divergence on both sides. Okay, so let's take, so which implies the divergence of this ai xt. So then pi j y t. Okay, so I have taken this divergence inside the commutator because it will only act on a. Clear? Everybody followed it? So that's equal to I delta ij. So clear? So the divergence is what? Can you tell me? What is divergence? Yes? Partial derivative with respect to x. Clear? So Shaman? Now how to do it? Okay, so divergence is, look here. So when I take del dot, or look at this very term. So this del dot, what does this divergence mean? Let's take this divergence of A. Can anyone tell me? So it means, let's say, partial I AI. So that means the index here. So if I am taking the index I here, so the index will come as what? I. So if I use the index J, then it will be index J. So that means the index here and here they get contracted. So divergence means that thing. So when I take the divergence, let's say, so d3k by 2 pi cube. So what is the index here? I. So it means it is the differentiation with respect to I e raised power minus I k dot x minus. So now let's take the differentiation with respect to x. So what it will bring down? Minus I k. What should be the index on k? I. So it is equal to I times delta ij integration delta 3k by 2 pi cube. So it is minus I k I. Okay, e raised power minus I k dot x minus y. So that means, so this has to be equal to 0, is it? By the definition, I am introducing this delta ij in such a way that this, when I take the divergence, this object is equal to 0. So what should I say? I and I this. Okay, so let me take this inside because there is an integration over k. So it is delta ij ki like this thing, e raised power minus I k dot like this. Okay, what I am saying, I am introducing a rank 2 tensor in such a way that once keeping the divergence there, so then the right hand also vanishes. So in other words, this must vanish. So for consistency condition, okay, this delta ij ki must be equal to 0. So got it? So this will give me actually the idea how to write this delta ij. Now we can write this delta ij like this. We can write delta ij as this delta ij minus ki kj by k square. Let's write this. Let's propose the form of what? This delta ij to be like this thing. Now let's check whether this condition is satisfied or not. So therefore, this delta ij ki is equal to delta ij ki minus ki kj ki by k square. So what this object is? So it is simply kj minus ki is k square. So kj k square. So what is that equal to? 0. So that means if I choose delta ij to be like this thing, then delta ij ki is equal to 0. So that means my right hand side now goes to 0 under divergence. So that means this kind of commutation is consistent with what? The gauge conditions. Provided this delta ij, this rank 2 tensor, has this kind of form in momentum space. Because this is in the momentum space. Okay, we have to put it in the coordinate space. समझ आओ? Got it? Okay, so let's write. Any question here? समझ आओ? Yes sir. जाओ. Okay, so let's write this thing. So what I am having, this integral. So I am having this integral d3k 2 pi q delta I j k I e raised power minus I k dot x minus y. This I can write like this thing. So d3k by 2 pi cube. Okay. Okay. Delta. Okay. What is this delta ij? And delta ij is like this thing. Or in other. Sorry. I will write this without this thing. I mean. So therefore we can write delta ij e raised power minus I k. So that this ki comes from the divergence, is it? So this is in the commutation, huh? Okay, so let me write. Okay, so let me write the commutation in this. Okay, so what is our commutation? Therefore, commutation relation. Equal time. I should say equal time, huh? So what is that? So you are having this AI xt. So and then you are having this pi j yt. So that's equal to I delta ij. Okay, integration d3k. Sorry. Okay, so let's write. So let me keep this delta ij inside it. Delta ij e raised power minus I k dot x minus 1. Can I write it? So delta function I put in the momentum space. Huh? Okay. So this is I integral d3k by 2 pi q. Okay, what is this delta ij? This delta ij minus ki kj by k square. Can I write it in this fashion? E raised power minus I k dot x minus 1. Okay? Can I write it? Okay. So this I can write I integral d3k by 2 pi q. Okay, so let's keep this delta ij as because it's nothing. So minus this I can write k I can, if I make a differentiation of this e raised power minus I k, so it will give me 1k, is it? So can I write it like this thing? Partial I, partial j. So when you take a partial j on this thing, what it will give me? Ki with a minus, is it? So when you take this thing, it will give me ki with a minus I. Okay. So minus and minus is plus I and I. So what it will be? It should be plus, huh? So it will give me actually plus sign, huh? So minus I into minus I is? So minus, no, it should be minus here. It cannot be plus, huh? Yes?
It will be minus.
Oh yes, there is one more term. So let me write this as nebulous. Okay, like this thing. So it is some, okay. So there that will, this term will cancel actually that minus. What this is? It's nebula square, 1 by nebula square. What it will give me? Minus 1 by k square, is it? So minus I k square it will give me. Yeah? So minus I square is minus, that minus will cancel with this thing. So therefore I can write it like this thing. I times delta ij minus partial I partial j by nebula square. Okay, integral d3k by 2 pi cube. Okay, e raised power minus I k dot x minus y. So what this object is? It's your Dirac delta function. Okay. So let me write it here. So therefore, so this is equal to I times delta ij minus partial I partial j by nebula square. Then I will write this as Dirac delta function x minus y. So if you see, this is actually the projection of the Dirac delta function along a transverse direction. So it is delta ij mean, okay, if you don't have this very term there, okay, then it is simply delta function, okay, 1 into delta function, clear? But there you are having this kind of object there. So we call this entire object as a transverse delta function. Okay. So let's call this transverse delta function as, so therefore the commutation is, our quantization condition is like this, delta 3 transverse x minus y. Okay, y. So we should put actually ij as well somewhere. Okay, so you can put ij, because the indices, because of the indices you put ij. So it itself means, when I put the vectors, it itself means what? It's a three-dimensional delta function. So you are having delta ij transverse minus. So it is simple. So it also comes from actually the Helmholtz theorem. Okay, so you can decompose a given vector into the transverse and the longitudinal components. Okay, so it is simply the longitudinal component, sorry, transverse component. Okay. So now you are having these quantization relations in the radiation gauge. In the radiation gauge, what you are having? So you have a quantization condition like this thing, but it is not Lorentz invariant. It does, when you say it is not Lorentz invariant, it does not mean you cannot calculate the physical quantities out of it. Okay, you can do all the calculations with it. Okay, in particular, okay, the physical results, physical reality is independent of the choice of a gauge. Okay, Samasha, or the physical reality is independent of the choice of a coordinate system. Choice of a gauge means choice of a coordinate system. Okay, Samasha. So you are, let's say if you are trying to calculate the scattering cross section, okay, that should be independent of the choice of the gauge. Okay, Samasha, that is what we mean by the gauge invariance of a system. Got it? Any question? So now let's go to the field decomposition quickly. Sorry, by 2, because we are in the next of units. So by 2. So this is actually the Hamiltonian. You can calculate it. How we calculate the Hamiltonian? PQ dot minus L. So what that is equal to? X pi mu A mu minus Lagrange. समझ आया? So you take mu equal to 0, pi 0 is 0. Clear? Or A 0 is 0. Then it will be pi I AI. Pi I is A dot. समझ आया? Sorry, it is A dot. Right? Then it will be A dot square minus L. From L you take the A dot. So you will get E square plus E square. Okay. Now let's take the field decomposition or the Fourier decomposition. Okay. So it's very trivial. The way we have done for the real scalar field and the complex scalar field or the Dirac field, it is the same thing here. We need to figure out what is the equation of motion in this very gauge. Okay. So what you are having the equation? Can you tell me what is the equation of motion? So what? Okay. So tell me. Yes. So it's simply anybody. So you are having partial mu mu is equal to 0. So for the timing, you will go to like this. Box operator acting on A nu, that's equal to 0, because there is no sources. There are no sources at all. So is this the thing what you can get? Huh? You sure? Okay. So what if you take nu is equal to 0? So what you will get? So if you take nu equal to 0, you are having A 0, that's equal to 0. So this is trivially satisfied because A is equal to 0. Because A naught is equal to 0. This identically satisfies it. Now that means, which implies therefore, for nu is equal to I is equal 1, 2, 3, other 3 components, you are having this box operator acting on AI is equal to 0. Is this the Klein-Gordon equation? without mass. What is the Klein-Gordon equation? So box operator plus mass phi is equal to 0. So that means this is for the massive particle. It means the photon satisfies the condition, the Klein-Gordon equation without mass. Samashyam? Got it? So this is a massless Klein-Gordon equation. Okay, so what should be the decomposition of? So it should be, the decomposition should be like that, the left moving wave and the right moving wave. Samashyam? But here, since it's not a scalar it's not a scalar field, it is actually a vector field because it is described by the vector A. Okay, so that means in the field decomposition I must incorporate the vector nature of the field, or these modes, left and right moving modes. Samashyam? So we denote those modes by the polarization of the field. Samashyam? So in other words, I can write the decomposition of this field A, okay, A of x like this, G3k by root of, in the same way what we have done in the earlier fields, twice omega k. I will use omega k. Omega k means the energy of the photon. Okay, so what is that? K times c, or c times k, the dispersion relation. And then you put actually summation over lambda, that's polarization. How many polarization degrees are here? 2 degrees, because in the radiation gauge only 2 degrees of freedom are there. Okay, so then I will write something epsilon lambda. Okay, so this is our polarization vector. Then you introduce actually the annihilation operator the same way what we have done for the scalar field. Okay, so that will depend on this lambda and k e raised to minus I k dot x. Then you are having this epsilon star lambda k a dagger lambda k e raised to I k dot x. Why k is the 4 momentum? This k is the 4 momentum of the photon. Okay. So we are having this k square. Okay, k square means what? K0 square minus vector k square, that's equal to 0. Samajh aaya? So this is the 4 momentum. K is the 4 momentum of photon. Okay. Samajh aaya? So if this is equal to 0, it means this k0 is equal to simply magnitude of k. Okay, or in other words, the energy of the photon is simply the momentum. So Samajh aaya? Okay, so remember this very point. Now what is our transversality condition? So this del dot A equal to 0 translates to what? Anybody? When you take the del dot A, so this term depends on x, is it? So it will bring down me k. Samajh? So because there is a divergence, which is the quantity, which is vector. So this epsilon is a vector quantity. Clear? So this del dot A will give me this k dot epsilon, that's equal to 0, and k dot epsilon star. So what does it mean? Polarization and the direction of propagation are transverse to each other. Samajh aaya? So that is the transversality condition. Okay, any question? Okay, and one more point. So since this is transversal, polarizations are also like this thing, orthonormal. So let me write k dot epsilon prime k. So that's equal to delta lambda lambda prime. So this is important condition. Okay. So this all about the quantization in the radiation gauge. Okay. So you can calculate now the energy using the formula for the energy density. Clear? So I will not do that. So those things we have already done. If you remember, the normal ordered Hamiltonian for the scalar field was what? Summation over that k, a dagger and a, is it? Then we calculate the Hamiltonian for the Dirac field. It was the energy contribution coming from the fermions and energy contribution coming from the anti-fermions. That was a dagger a, sorry, f dagger f plus f tilde dagger f, is it? So now you are having what kind of modes here? What kind of operators? A and a dagger. What should be the energy? So the energy here, I can calculate the normal ordered energy. So that's equal to, since each mode will contribute the energy, I mean each polarization, so it is something G3k, okay? Let me write omega k, a dagger, lambda k, okay? A lambda k. So this is the energy in the field modes. That means you have decomposed the system of, the electromagnetic field you can represent as the sum of the infinite number of harmonic oscillators. Samajh? If you see all the kinds of fields what we have described till now, we have decomposed them into the harmonic oscillators, is it?
Yes, sir.
So that's why harmonic oscillator is very fundamental in nature. Everything fundamentally is like what? A harmonic oscillator. Samajh? Got it? Shall we stop here? Or?
Yes, sir.
Okay. So we'll do the Feynman rules in the next lecture.